Hey, chemistry. I want to talk through the next two periodic trends with you. So this is periodic trends part 2. We're going to talk through electronegativity and ionization energy. So let's start with ionization energy. Okay, so remember, ionization energy is the energy required to pull off an electron from an atom. So you can think about it as if you had a log and you were trying to break a branch off of that log. How much energy would you have to put in order to break that little piece off of the whole? So it's a measure of energy required. Okay, and this is going to come down to the same type of forces that we've been talking about this whole time. Remember, there's this driving force of attraction, and that force of attraction is dependent on charge and distance, right? So charge, we're going to put on top, and then distance is going to be on bottom, and distance is actually squared. So distance makes more of a difference than an increase in charge would. So this is getting back to the same factors we were talking about in the Coulomb's force of attraction. So charge, if you increase charge, it's going to increase the force of attraction. If you increase distance, it's going to decrease the force of attraction. Charge and force are directly proportional. Distance and force are indirectly proportional. So with these things in mind, let's think through ionization energy. And again, we're going to use this second row of the representative elements as our row, as our example, as our row to look at. So if we are looking left to right among the rows, so we're comparing lithium all the way to neon, how do you think ionization energy is going to change? Why don't you pause the video here and give yourself a prediction? Is ionization energy going to increase or decrease? Okay, so if we're looking at these two forces, distance really isn't going to change much at all. Distance does change across this row a little bit. Remember, lithium is going to be bigger than neon, and so we're going to be decreasing in distance. As we decrease in distance, we're going to need more and more and more energy to overcome that larger and larger and larger force of attraction, right? Along with the slight decrease in atomic radius, however, comes a really significant increase in nuclear charge. So if we look at the nuclear charge, we represent nuclear charge with a Z, by the way, fun fact of the day. So if we look at nuclear charge for all of these, lithium's a 3+, beryllium 4, 5, 6, 7, 8, 9, 10, basically nuclear charge is just looking at electrons, right? So we have an increasing nuclear charge, and actually from lithium all the way to neon, it more than triples. The nuclear charge more than triples within this row. And so as the Z effective, or as the nuclear charge is getting stronger and stronger, we're going to need more and more energy to remove that electron. So ionization energy, or the energy required to remove an electron, is going to increase from lithium to neon. So it's going to go this direction. It's going to start small. Ionization energy will be smaller for lithium. It will be bigger by the time you get to the end here with neon. And that's going to be due to an increasing nuclear charge. Okay, let's look top to bottom now. Okay, if we're looking at one family, so hydrogen through sodium, if we're going top to bottom, how do you think ionization energy is going to change? Stop here and make a prediction. So the factor that's changing here, we definitely do have an increasing nuclear charge, right? Hydrogen is +1, lithium is +3, sodium is +11. We definitely do have an increasing nuclear charge, which is going to increase ionization energy, but we also have increasing distance. So hydrogen has 1 energy level, lithium has 2, sodium has 3. So that outermost electron that we're looking at removing for ionization energy, that outermost electron is getting farther and farther and farther away from the nucleus. And remember, when we're looking at Coulomb's attraction, that force of attraction, charge is definitely going to increase the force of attraction. Distance is going to decrease the force of attraction, but distance is actually squared. So distance makes more of a difference than charge makes. And so ionization energy, as you go from the top to the bottom, it's actually going to decrease. Hydrogen's ionization energy is going to be the largest. You're going to need the most energy to remove the electron from the hydrogen atom. Sodium, and then continuing down that family, is going to be the smallest, all the way down to francium down there, because as that electron moves away from the nucleus, you're going to need less energy to remove it from that atom. So ionization energy is going to decrease top to bottom because of an increasing nuclear atomic radius. Okay, so those are your 2 periodic trends for ionization energy. Why don't we pause here and we can do a little check-in. Rank phosphorus versus nitrogen for me. Which of those is going to have a larger ionization energy? And then let's do oxygen and fluorine also. Which of those is going to have a larger ionization energy? Check in. Okay, now we get to talk about electronegativity. Okay, so remember, electronegativity is the force of attraction between the nucleus and an electron that it is trying to attract. So we're not talking about a nucleus and its own electrons. We're talking about a nucleus and an electron that's on a different atom or in a different system that the nucleus is trying to attract. How strong can that nucleus attract another electron to itself? So this is very, very close to Coulomb's attraction, right? In Coulomb's attraction, we were talking about a force of attraction and how it is proportional to charge, and it's indirectly proportional to distance. Okay, so this little relationship here, we're going to be describing that almost exactly. The only difference is you need to remember that it's the nucleus attracting an electron that does not already belong to it. Okay, so let's take a look in our period. What is this trend going to look like in our example of the second row? From lithium to neon, will electronegativity increase or decrease? Pause here and make a prediction. So the charge is going to be our dominant force here. Yes, distance is going to change, but distance is going to change fairly slightly. Charge is going to change greatly. We just looked at this with ionization energy, where our nuclear charge is going to more than triple between lithium and neon. And so our charge is going to be our driving force here, our deciding factor here. And because charge is increasing, the atoms are going to be more and more and more able to attract electrons to itself. So electronegativity for lithium is going to be fairly low. Electronegativity for neon is going to be, actually for fluorine, is going to be fairly high. So electronegativity is going to increase when you're going left to right in a period. Now, I almost misspoke there, and I was talking about neon for a second. Now, neon certainly follows the trend where it has 10 protons, right? It has a lot of nuclear charge there. However, remember that neon's shells, it's 1s shell, it's 2s and 2s shell, so its first energy level and its second energy level are actually perfectly full with electrons. They both have a full electron level. They have that full octet of electrons, and it gives neon this special stability. So neon actually doesn't attract other electrons to it at all. But it's not because of the charge or distance, it's because of the special stability that happens when you fill those energy levels. And so for electronegativity, we actually kind of ignore neon. We ignore all the noble gases because they kind of break our trends for reasons that are outside of the force of attraction, outside of Coulomb's force of attraction. So we're just considering lithium to fluorine here. And between lithium to fluorine, electronegativity is going to increase, and it increases because of an increase in nuclear charge. All right, let's look top to bottom. What is electronegativity going to do inside any given family? So again, we're just going to look at the first column as our example, but this would be true for any family that we would want to look at. So take a minute, make a prediction. Hydrogen to sodium, is electronegativity going to increase top to bottom, or is it going to be decrease top to bottom? Okay, again, we have increasing charge, but we also have increasing distance because of those increasing energy levels. And so top to bottom, electronegativity, or the force of attraction, the ability for the nucleus to attract an electron that's outside of the atom, is actually going to decrease. So the farther and farther and farther away that open orbital gets, the less the nucleus is able to attract an electron into that open orbital. And so electronegativity will decrease from the top to the bottom. Hydrogen will have the highest electronegativity. Sodium will have a lower electronegativity. And it's going to decrease because of increasing size and increasing atomic radius. All right, so let's do a quick check-in here. Let's again compare nitrogen to phosphorus. Which one's going to have the largest electronegativity out of those two? And then let's compare, let's do boron and carbon in this case. Which one is going to have the largest electronegativity between boron and carbon? All right, and those are our main periodic trends. We've done atomic radius, we've done ionization energy, and we've done electronegativity. So let's do a little practice with that. Send me your questions, and then once we get into talking about ions, we're going to return to the periodic trends and talk about how they change slightly for an ionic radius. All right, let me know what questions you have. I will see you in class.